Hi everyone. Now we are at Eigenvalues and Eigenvectors, lecture number 7. So first I will discuss about adjacency of a matrix. Then I will enter into main topic. So first adjacency of a matrix. You have seen this one in PUC. Okay. Let me just recall it. For 2 by 2 matrix, how to find adjacency matrix? So for 2 by 2 matrix, 2 by 2 matrix. So for example, let's take the matrix A is A, B, C and D. So this is 2 by 2 matrix. Then how to find adjacency matrix? Directly. So these two will interchange, right? So D will be here and A will be here. And it is defined like this. It is not by formula or something else. The adjacency matrix is defined like this. Okay. And here sign changes, minus B and here minus C. So this is for 2 by 2 matrix. What I have to do? These two have to be interchanged. Okay. And these two will be sign changes. Okay. That's what minus B. If it is minus B, it should be plus B, like that. And for 3 by 3 matrix, cofactor matrix we need to find. Okay. So let us take one arbitrary 3 by 3 matrix. So let us call the matrix A is A, B, C, D, E, F, G, H, I. Let us call this. This is 3 by 3 matrix. And for this we want adjacency matrix. Okay. So then adjacency of the matrix is defined. So before that, we need to find the cofactor matrix. So let assume the matrix B is how to find the cofactor matrix. You know already, just I am recalling, nothing else. So here the first entry should be the, with respect to A, the determinant we need to find. So with respect to A, the determinant is this one, right? So that means this row. So this column, this row will disappear, and this determinant we need to calculate. E into I minus H into F, like that. So first entry minus 1 whole to the power of I plus J, right? I plus J. I means rows, J means columns. So what is the address of first element A? A is in first row and first column. So first row plus first column. And its determinant is EI minus FH. F into H. Like this. Okay. Similarly, the second entry is, what is second entry? With respect to B, we have to expand. With respect to B. Okay. With respect to B. That means, with respect to B, we have to expand. So this one and this one will go. So determinant D into I minus F into H, like this. So with respect to B, we are expanding. So minus 1 whole to the power of. So what is the address of element B? That is in first row and second column. First row and second column. That's why 1 plus 2. Minus 1 whole to the power 1 plus 2. And the number is, the det is D into I minus F into G. F into G. This one. Okay. Similarly, next one, with respect to C, we have to expand. Okay, with respect to C. With respect to C, we have to expand. So with respect to C. Again, this column, this row will disappear, and this det we need to write. So with respect to C, what is that? Minus 1 whole to the power of. So what is the address of C? It is in first row and third column, 1 plus 3. So what is the det? D into H minus E into G. Like this. So it is over. Similarly, next entry. So this entry how to find? The same story. So now with respect to D, we have to expand. With respect to D. Here with respect to D, we have to expand. D. So with respect to D, what is the address of D? Minus 1 whole to the power of. D is in second row, first column. Second row, first column. Okay. and corresponding rate. So D is in first column, second row, this will disappear. So B into I minus H into C. B into I minus H into C, like this. Okay, and next, with respect to E, we have to expand with respect to E. So this with respect to E I want. What is the address of E? Minus 1 whole to the power of I is in second row, second column. Second row, second column, 2 plus 2. So minus 1 whole to the power of 4 is 1 only. Okay. And the debt is, what is the debt? A into I minus J into C. A into I minus J into C. Like this. So similarly, this entry, this entry, this entry, and this entry we can calculate. So this is B. Then next one we need to compute B transpose. Just transpose it. So therefore, we are then now adjoint matrix of the given matrix A is simply B transpose. So this is a way of finding adjacency matrix. Okay, for 2 and 3 by 3. And for 3 by 3, same story. 3 by 3. So if it is 4 by 4 matrix, 4 by 4 matrix, same ideology we have to apply, same ideology. With respect to this, the debt we need to find the remaining 3 by 3 matrix debt. You know how to find 3 by 3 matrix determinant. Here 2 by 2 matrix determinant we are calculating because it is 3 by 3 matrix. Okay, like that. So this is about adjacency matrix. The concept I will use in the coming lectures. Okay. Next one new topic, diagonalization of a matrix. So in this topic we are going to learn how to diagonalize a matrix depending on eigenvalues and eigenvectors. Okay. Now first definition. A square matrix A is of order n. That means it is n by n order matrix. Okay. Over a field F. Field F means the entries coming from F. F may be real number system, complex numbers, and that matrix is said to be diagonalizable if it is similar to a diagonal matrix over the same field. It is similar to a diagonal matrix. What is the example of diagonal matrix? For example, diagonal matrix example is 1 0 0 0 1 0 and 0 0. This is a diagonal matrix. Okay. If any matrix is similar to this matrix, that is called diagonalizable matrix. But under what condition it is diagonalizable, we will see now. But it is similar to like this kind of diagonal matrix only. Okay. Next one theorem. Theorem number 1. If a square matrix A has distinct eigenvalues, then the matrix A is diagonalizable. Distinct eigenvalues. Here this is main distinct eigenvalue. The immediate conclusion is the matrix A is diagonalizable. Problem number 1. Show that the matrix 2 by 2 matrix is diagonalizable matrix, and find the diagonal matrix. Okay. So based on the theorem number 1, when can I say that it is diagonalizable? If a square matrix A has distinct eigenvalues, right? So then find the eigenvalues first to this 2 by 2 matrix. Find the eigenvalues first. Okay. Yeah, calculate eigenvalues. After that we will decide it is diagonalizable matrix or not. So how to calculate eigenvalues? So first I want eigenvalues. Okay. Then determinant of A minus lambda I. Characteristic equation, right? We have to solve characteristic equation for eigenvalues. What is A? A is 2 by 2 matrix 3 4 4 3. Okay. Minus lambda times, since it is 2 by 2 matrix, identity matrix also 2 by 2 matrix 1 0 0 1 is equal to 0. Now this is, simplify this, 3 minus lambda 4 4 again 3 minus lambda is equal to 0. Okay. Now let us find the determinant. So 3 minus lambda into 3 minus lambda minus 16. So 3 minus lambda, so lambda minus 3, so 3 3 is a 9, minus 3 lambda, next minus 3 lambda next plus lambda square, okay, and minus 16 is equal to 0, and first highest power is 2, so lambda square term is first, next minus 6 times lambda, next minus 16 plus 9, so minus 7 is equal to 0, okay, and yeah, let us find the eigenvalues. You can factorize or simply uh, use the formula minus b plus or minus b square minus 4. See here I am using the concept of factorizing. So it will be minus 7 lambda plus lambda I am writing. So that if you do the club, you will get minus 6 lambda. And if you do the multiplication, minus 7 will get. Perfectly satisfying. So then let us drag lambda outside. So lambda minus 7 and plus 1 is common. Lambda minus 7. So overall lambda plus 1 into lambda minus 7 is equal to 0. So therefore lambda 1 is equal to 1 and lambda 2 is equal to 7 are the eigenvalues of the matrix A, given matrix A. Okay, if you call this matrix A, eigenvalue of that matrix. Okay, and next, so one question, show that the matrix is diagonalizable. So therefore we are getting distinct eigenvalues. Therefore distinct eigenvalues existed. Distinct eigenvalues existed. Therefore the given matrix is diagonalizable. Okay, and next question is find the diagonal matrix. So therefore diagonal matrix is simply the eigenvalues are the diagonal matrix. Eigenvalues should be in the principal diagonal. Okay, diagonal matrix is equals to, so what are the eigenvalues? Lambda 1 is the first eigenvalue and second eigenvalue is lambda 2. So this is nothing but 1 0 0 7. So this is a diagonal matrix. That's it. So this is a diagonal matrix of the matrix 3 4 4 3. Okay, so this is a way of concluding the given matrix is diagonal or not. If the matrix having not distinct eigenvalues, for example eigenvalues are repeated, then we cannot conclude so far. Okay, only you can conclude if it is having distinct eigenvalues, then only you can conclude it is diagonalizable matrix. Clear? Next one, problem number 2. Does the matrix 3 by 3 matrix is diagonalizable matrix? If so, find the diagonal matrix. Again same story, since it is what kind of matrix it is? Lower triangular matrix, right? So since it is lower triangular matrix, the diagonal entries are nothing but the eigenvalues. So since the given matrix is lower triangular matrix, lower triangular matrix, therefore eigenvalues are the diagonal elements. Or simply you can calculate by using characteristic equation. Find the characteristic equation and solve it, you will get the eigenvalue. That's another way of doing it. Okay. So therefore lambda 1 is equals to 4, okay, and lambda 2 is equal to 2 and lambda 3 is equal to 3 are the eigenvalues. These are the diagonal entries, right? Eigenvalues. So these are the diagonal entries 4, 2, 3. So these are the eigenvalues since it is lower triangular matrix. For upper triangular matrix also, diagonal entries are nothing but the eigenvalues. So now, what is our question? Does a matrix is diagonalizable matrix? So since here, since all the eigenvalues are distinct, all the eigenvalues are distinct, therefore the given matrix is diagonalizable. Diagonalizable. Okay. And if so, find the diagonal matrix. What is the diagonal matrix? So therefore, diagonal matrix is, what is the diagonal matrix? Simply lambda 1 0 0 0 lambda 2 0 and 0 0 lambda 3. So this is the diagonal matrix. Simply eigenvalues will sit in the principal diagonal, on the principal diagonal. So 4 0 0 0 2 0 and 0 0 3. So this is the diagonal matrix. Okay. Next one, note converse of the above theorem number 1 is need not be true. What is the converse actually? Theorem number 1 is need not be true. Therefore, the statement is this: if the matrix A is diagonalizable, then the matrix A may not has distinct eigenvalues. Example is, let's try this one example. Example. So consider this matrix 3 by 3 matrix 1 0 0 0 1 0 0 0 1. Now look at in this, since it is triangular matrix, right? It is both upper triangular matrix and lower triangular matrix. So therefore, the entries which are sitting on the principal diagonal are said to be eigenvalues. Therefore, clearly eigenvalues are lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to 1. Or you find the characteristic polynomial or characteristic equation. For the characteristic equation, a minus lambda I equal to 0. If you solve this, what you will get? What is a minus lambda I? 1 minus lambda, 1 minus lambda, 1 minus lambda. All entries are zeros. Then if you do the determinant, you will get lambda minus 1 whole cube. Okay. Lambda minus 1 whole cube, which is nothing but all are ones. So all eigenvalues are ones. That means it is repeated. Okay. Eigenvalues are repeated. But can I say that, does it diagonalizable? Yes, it is diagonalizable. Look at, it is diagonalizable. Okay. So this is the best example. For the converse of the theorem is need not be true. Next one. So now diagonalization of a matrix with repeated eigenvalues. How to uh, conclude that a matrix is diagonalizable if repeated eigenvalues are existing. Okay, let us enter now. So before entering into this, we need to know two concepts. One is algebraic multiplicity, and the second one is geometric multiplicity. So by using these two concepts, we can decide whether the given matrix is diagonalizable or not. First, algebraic multiplicity. So let lambda 1, lambda 2 up to so on lambda n. This is lambda n. This is lambda n. Okay. lambda 1 to lambda n are eigenvalues of an n by n matrix A. Since A is an n by n matrix, therefore n eigenvalues exist. And f of lambda be a characteristic polynomial of the matrix A. Okay, and which is this one, f of lambda. So this is a characteristic polynomial, lambda minus lambda 1 whole to the power of k1, lambda minus lambda 2 whole to the power of k2 up to so on, lambda minus lambda n whole power kn. This is a characteristic polynomial. So then the algebraic multiplicity of the eigenvalue lambda 1, first eigenvalue, this is the first eigenvalue. So this is the first eigenvalue lambda 1. So its algebraic multiplicity is power k1, right? So k1. That means k1 times lambda 1 is repeated. Its meaning is that algebraic multiplicity means. And lambda 2, how many times it is repeated? K2 times. Okay, in previous example, identity matrix I have taken 3 by 3 identity matrix. So what is the characteristic polynomial there? Lambda minus 1 whole cube whole to the power of 3. Therefore the eigenvalue 1 is repeating 3 times. So therefore the eigenvalue 1 is having algebraic multiplicity 3 there. So here k1 means 3 there. Okay, I will give some examples for making clear. Similarly, lambda 3 is repeating k3 times. Therefore, eigenvalue lambda 3 having algebraic multiplicity 3. Similarly, up to so on, lambda n having algebraic multiplicity kn. So this is algebraic multiplicity. So to know the algebraic multiplicity of all the eigenvalues of a matrix, first we need to know what is a characteristic polynomial or characteristic equation, whatever. In that characteristic polynomial, we can find what is algebraic multiplicity of each and every eigenvalue. Okay, look at this example. So first one, look at this is a characteristic polynomial of a matrix. Okay, so total how many eigenvalues are existing? 2 is repeating 3 times. Indirectly 3 eigenvalues are present here, and here 1 is repeating 2 times. That means 2 eigenvalues are existing here. Total how many? 5. And this one is 6. So this is 6 by 6 matrix characteristic polynomial, because total 6 eigenvalues are existing. Clear? Indirectly what are the eigenvalues here? Eigenvalues are 2 comma 2 comma 2, 2 is 3 times, 1 1 1 is 2 times, and this 3 is 1 time. Look at 6 eigenvalues are existing. Therefore it is 6 by 6 matrix characteristic polynomial. Okay, similarly this one here, what are the eigenvalues now? Minus I is first eigenvalue, second eigenvalue is 2. Okay, now solution. First one, eigenvalues are how many? Distinct eigenvalues are 3, 2 1 3, right? So total number of eigenvalues are 6. So first eigenvalue 6, eigenvalue 2. So for this, what is algebraic multiplicity? Algebraic multiplicity AM is how many times? So here what is k1? K1 is 3 here. So algebraic multiplicity of the eigenvalue 2 is how much? 3. That means 2 is repeated 3 times. Similarly, eigenvalue 1. So eigenvalue 1. What is algebraic multiplicity? Algebraic multiplicity of the eigenvalue 1 is how much? 2, because it is repeated 2 times. Look at the power k2 is 2 here. Next one, eigenvalue, third eigenvalue 3, third distinct eigenvalue. Okay, now what is algebraic multiplicity? Algebraic multiplicity of the eigenvalue 3 is only one time. It is only one, power 1, right? K3 is 1 here, power is 1 here, nothing there means 1 here, K3 is 1. So these are the algebraic multiplicities. Okay, similarly number 2, second one, the second problem, algebraic multiplicity of the eigenvalue minus I, how much? It is 1. Next, algebraic multiplicity of the eigenvalue 2, how much? 1. Look at the powers are here, nothing is there, here is 1, power is 1. So these are called algebraic multiplicity. Okay, next one, geometric multiplicities. Okay, let A be an n by n square matrix then geometric multiplicity of an eigenvalue lambda is nullity of A minus lambda I. Nullity means 0 rows. Okay, here nullity means 0 rows. Nullity means number of 0 rows. Number of 0 rows. That means a row consisting entirely zeros. That is called 0 row. A minus lambda I, or simply n minus rank of A minus lambda I. N minus rank of A minus lambda I. Both are same. So this is about geometric multiplicity. Let's have one problem. Then with this it will be very clear. Now look at. Question is, find the geometric multiplicity of all the eigenvalues of this matrix. So first, what are the eigenvalues we want? So find the characteristic equation, or simply look at, this is an upper triangular matrix, right? So since A is upper triangular matrix, A is upper triangular matrix, therefore eigenvalues of A are its diagonal entries. Its diagonal entries. So now what are the diagonal entries here? 3, 3, 4. So these are the diagonal entries 3, 3, 4. So therefore lambda 1 is equals to 3, lambda 2 is equal to 3, and lambda 3 is equal to 4 are the eigenvalues. So eigenvalues we got. Next, what do you want after that? We want geometric multiplicity, right? So what is geometric multiplicity? Geometric multiplicity of an eigenvalue lambda is nothing but nullity of A minus lambda I or n minus rank of A minus lambda I. So first we want nullity or first eigenvalue 3, right? So I want geometric multiplicity of 3. So first eigenvalue 3. So this one, for this I want geometric multiplicity. Okay. Then so lambda is 3 indirectly, right? So A minus lambda I, okay, matrix A minus lambda I is nothing but A minus 3i, because lambda is 3 here. What is A minus 3i now? Which is matrix A. Matrix A is 3, 1, 0, 0, 3, 0, 0, 0, 4. Minus 3 times identity matrix. Since A is 3 by 3 matrix, identity matrix should be 3 by 3 of order. So 0, 1, 0 and 0, 0, 1. Okay. Now this will be, simplify this. What do we get? So 0, 1, 0, 0, 0, 0, 0, 0, 1. And this is similar to interchange second row and third row. If you interchange second row and third row, that means R1 is interchanging to R2. Sorry. R2 is interchanging to R3. Then what do you get? 0, 1, 0, 0, 0, 1. It's not required. Interchanging is not required. Just to make it very clear, I'm telling you. This step is not required. And now, so therefore, conclusion. So therefore, geometric multiplicity. So GM I'm writing. Geometric multiplicity of the eigenvalue 3. How much? Simply according to the definition, nullity of A minus lambda I. Nullity means number of 0 rows. What is the number of 0 rows here? Only 1. So therefore, 1. Or you can conclude like this also by second. So geometric multiplicity of 3, yeah, By using this n minus rank of a minus lambda I, right? Look at this definition, n minus rank of a minus lambda I. So what is n here? N means, what is n? A be an order n by n. So here a be an order of n 3 by 3. So n is equal to 3, right? So 3 minus, okay. So simply you write the formula without confusion. Write this. Yeah. So you can conclude like this, n minus rank of a minus lambda I. So a minus 3i indirectly. Lambda is 3 here, right? So which is nothing but what? N is what? N is 3 here minus rank of a minus 3i. What is the rank of this? Number of non-zero rows. Number of non-zero rows are 2. So rank is 2. Indirectly 1. You can conclude like this or like this, your wish. Any of the way you can conclude. Okay. So this is geometric multiplicity of the eigenvalue 3. Okay. Next, second one. Second eigenvalue. So eigenvalue or geometric multiplicity of the eigenvalue. What is eigenvalue? Next one is 4. Okay. Now, yes. So a minus lambda I, which is nothing but a minus, what is lambda here? 4. A minus 4i. So directly I am writing a minus 4i. What is a? This is a minus 4i. 4 we have to subtract. So minus 1, 1, 0, and 0, minus 1, 0, and 0, 0, 0. So subtracting 4, right, from the diagonals. Now, can you make this row, second row, can you make it 0? You cannot make it 0. If you club these two, again this entry will become present. So this row you cannot make it 0. You have to simplify the matrix. Remember, for example, if you are having like this, tell this. See, for example, you got like this 1, 1, 0, and 2, 2, 0, and 0, 0, 0. Like this you got, for example. Okay, like this you got. And don't think that number of 0 rows is 1, so therefore nullity is 1, therefore algebraic multiplicity is 1. That is wrong. You look at second row also you can make it 0. How to make it 0 second row? R2 is modifying as R2 minus 2 times R1. If you apply this row operation, it becomes 1, 1, 0, 0, 0, 0, 0, 0, 0. It means after simplification you have to decide. That's what, look at the definition. Rank of A minus lambda. Rank means what? How to collect rank? First you have to convert the matrix, this matrix into reduced echelon form. Then you have to look at number of non-zero rows. Okay, similar here also. Nullity means number of non-zero rows. Let me clear it. Number of non-zero rows in reduced echelon form. In reduced echelon form. Now it is very clear. Reduced echelon form. Reduced echelon form of not A. Reduced echelon form of A minus lambda I. Complete A minus lambda I. Okay. So like this. So now here, so therefore, conclusion is, therefore, what is the nullity now? Nullity is number of 0 rows. How many number of zeros? 1. So therefore, geometric multiplicity of the eigenvalue 4 is how much? 1. Geometric multiplicity is 1. Or simply by looking at the second definition, n minus rank of A minus lambda I. Or you can look at like this, n minus rank of A minus lambda I. Lambda I means 4i, minus 4i. Okay, minus 4i. What is n here? 3, minus rank of A minus 4i. What is the rank? 2. So 3 minus 2 is equal to 1. Either that, by using this definition or this definition, whatever, we follow any one of the definition, we will get the geometric multiplicity of the eigenvalue, corresponding eigenvalue. Next one, theorem number 2. A square matrix A is said to be diagonalizable if and only if the algebraic multiplicity and geometric multiplicity of all eigenvalues of A are equal. Okay, so if the eigenvalues are not repeating, no problem. If all the eigenvalues are distinct, directly we can conclude that the matrix A is diagonalizable. If the eigenvalues are repeating, then this theorem is useful. If the eigenvalues are repeating, how to decide? You look at the eigenvalues and find the geometric multiplicities and algebraic multiplicities of all the eigenvalues. If these two are same for each and every eigenvalue, then the corresponding matrix is diagonalizable. Okay, let's have one problem, then it will be very clear. Problem number 4. Does the matrix is diagonalizable? Okay. Yeah. Now, what are the eigenvalues? Since it is upper triangular matrix, so diagonal entries are nothing but eigenvalues. So therefore, since A is upper triangular matrix, so if it is not upper or lower triangular matrix, compulsory we need to find what are the eigenvalues first. Okay, by using characteristic equation. So therefore, lambda 1 is equals to 3, lambda 2 is equal to 3, and lambda 3 is equal to 4 are the eigenvalues. Okay, are the eigenvalues. Yeah, once eigenvalues are obtained. Next, what do we want to conclude is diagonalizable. So look at eigenvalues are repeating. So now this theorem is useful. We need to find geometric multiplicity and algebraic multiplicity of all the eigenvalues. So first heading is eigenvalue 3. For eigenvalue 3 I am finding. Eigenvalue 3 I am finding. So for this 3, what I want? Algebraic multiplicity I want. Okay? Algebraic multiplicity. So how to get algebraic multiplicity? I want characteristic equation, right? Characteristic polynomial a minus lambda I. So this is nothing but, since the eigenvalues are 3, 3 lambda, therefore characteristic polynomial, can you guess? Lambda minus 3 into lambda minus 3, or simply you can calculate because a is already given, then find the det you will find, and lambda minus 4. So this is nothing but lambda minus 3 whole square into lambda minus 4. So this will be the characteristic polynomial because 3 is repeating 2 times and 4 is repeating 1 time. So now this is a characteristic polynomial. Therefore, what is algebraic multiplicity of the eigenvalue 3? What is that? It is repeating 2 times. Therefore, algebraic multiplicity is 2. That's it. We are finding only eigenvalue 3. That's it. Okay. Next, geometric multiplicity I want. For geometric multiplicity, what do we want? Again, by the definition, nullity of a minus lambda I want, right? So therefore, this is geometric multiplicity. So this algebraic multiplicity. Next, we want geometric multiplicity. Okay. Yeah. Next, a minus 3 I want matrix a minus lambda I. First, let me write lambda I, and which is nothing but a minus, what is lambda here? Lambda is 3i. Okay. This is nothing but matrix A 3 1 0 0 3 0 0 0 4. So this is matrix A minus 3 times identity matrix 1 0 0 0 1 0 0 0 1. Okay, now simplify this. What will get? The new matrix 0 1 0 0 0 0 and 0 0 1. Okay, 4 minus 3 1. So therefore, what is the conclusion now? So therefore, is it reduced echelon form? If you want, you can proceed to the next step, or directly can conclude here also, no problem. So 0 1 0, interchange these last two rows 0 0 1 and 0 0 0 0 0 by interchanging r 2 with R3. R2, R3 interchanging. So that I got this one. So this is similar to this. Now this is reduced echelon form matrix, and in this, therefore, what I want n minus or that are simply nullity of a minus 3i. So which is 1. So nullity is number of 0 rows, right? Number of 0 rows is only 1. So nullity is 1. So therefore look at algebraic multiplicity of 3 is 2. But therefore what is geometric multiplicity here? So geometric multiplicity of the eigenvalue 3 is how much? 1. Okay. So both the multiplicities we calculated, algebraic multiplicity and geometric multiplicity. But according to theorem, a square matrix A is said to be diagonalizable if and only if algebraic multiplicity and geometric multiplicity of all eigenvalues should be equal. But here 3 for 3 it is not equal. Therefore no need to compute for the eigenvalue 4. You can stop here the calculations. So immediately therefore what is the conclusion? Therefore, since algebraic multiplicity and geometric multiplicity of the eigenvalue 3 is not same, therefore the matrix is not diagonalizable. So therefore algebraic multiplicity of the eigenvalue 3 is not equals to geometric multiplicity of the eigenvalue 3. So therefore by theorem number 2, the given matrix A, is not diagonalizable. Okay. So this is a final conclusion. If it is diagonalizable, we can write what is its diagonal matrix. What are the diagonal matrix? All the eigenvalues should sit on the principal diagonal. Okay. Next one. Problem number 5. With this, I will stop the session. Last problem. Does the matrix A is diagonalizable? If so, find its diagonal matrix. Again, same story. Yeah. So first I want eigenvalues. So here compulsory I need to find eigenvalues because it is not upper or lower rectangular matrix, right? So first I want eigenvalues. Eigenvalues I want. Then determinant of A minus lambda I equal to 0. This characteristic equation. So by using this, we can find what are the eigenvalues. So that implies yes, A 1 1 1 0 1 0 0 1 2. This is A minus lambda into identity matrix 1 0 0 0 1 0 and 0 0 0 0 0 1. Okay. That is equal to 0. Yeah, simplify. So determinant of 1 minus lambda 1 1. Next 0 1 minus lambda 0. Next 0 1 2 minus lambda is equal to 0. Now find the determinant 1 minus lambda into expand through this entry 1 minus lambda. So 1 minus lambda into 2 minus lambda. 1 minus lambda into 2 minus lambda. Okay. And minus 0. Next one through 1 minus 1 into 0 into this 0 and 0. So 0 minus 0. Next plus 1 into through this entry. 0 into 1 0 and 0 into 1 minus lambda is 0. So 0 minus 0 equal to 0. Now expand it. So 1 minus lambda into 1 minus lambda into 2 minus lambda equal to 0. Okay. So take one minus common in each and every bracket. So lambda minus 1. So minus into lambda minus 1 into lambda minus 1 into lambda minus 2. So 1 minus will comes out, and 2 minus minus into minus become plus. So overall multiply both sides with 1 minus. So lambda minus 1 whole square into lambda minus 2 equal to 0. So this is characteristic equation, or you can find characteristic polynomial also, no problem. Okay, then for each and every eigenvalue we want what is algebraic multiplicity and as well as geometric multiplicity. Therefore what are the eigenvalues? Therefore lambda 1 is equals to lambda 2 is equals to 1 comma lambda 3 is equal to 2 are the eigenvalues of the given matrix A. Okay, then come to the algebraic multiplicity of each and every eigenvalue. So first eigenvalue so for this I want to find algebraic multiplicity and geometric multiplicity. Okay, first algebraic multiplicity. Algebraic multiplicity of eigenvalue 1 is how much? Power k1, right? So here what is the characteristic polynomial? Look at this is a characteristic equation, or this one is characteristic polynomial. Look at 1 power 2 is there, right? So this is 2, k1 is 2. So therefore clearly algebraic multiplicity of the eigenvalue 1 is 2. Next I want geometric multiplicity, right? So for that what I want again? Then I want a minus lambda I. I want nullity, right? Or rank of n minus a minus lambda I. N minus rank of a minus lambda I, right? A minus lambda I is equals to a minus lambda is here 1. So 1 into I, identity matrix. Okay. And which is matrix A. What is matrix A? 1 1 0 1 1 0 and 0 1 0 0 1 0 and 0 1 2 0 1 2. This is matrix A minus 1 into I, identity matrix 1 0 0 0 1 0 0 0 1. And what is this now? Opposite location 1 minus 1 0 and 1 0. Okay, and 0 0 0 and 0 1 1. Again this one if you want you can modify, or you can keep like this, no problem. This step is not required. What I am doing is R3 is modifying now, R2 is modifying as R3 minus R1. Now this become 0 1 0 0 0 0 0 0 1. After that you interchange these two rows. I am not doing much more, and here I can conclude directly. Therefore so therefore geometric multiplicity of geometric multiplicity of the eigenvalue 1 is nothing but n minus rank of, or simply nullity also can add, your wish, a minus lambda I. Lambda is 1 here, so 1 into I. Okay, so which is nothing but n means here 3 by 3. A is of order 3 by 3, so n is 3 minus rank of a minus I. So this is the matrix. What is the number of non-zero rows here? 2. So finally it is 1. Okay, look at here, algebraic multiplicity of 1 is 2, but geometric multiplicity of the same eigenvalue is 1, not equals to. Okay, so therefore algebraic multiplicity of the eigenvalue 1 is not equivalent to, so it is not equivalent to I think matrix A we have substituted wrong here, right? What is the matrix? Let me go back. Triple ones, right? Here triple ones, but I have taken wrong here. Yeah, let me rectify this. So yeah, so this is not 0, this is 1, right? So this is 1. This is matrix A, right? And this become 1, right? So become, yeah, so everything will be changed now. Yes. So 1 0 0, this is fine, and but here it will be 1, and r remains r1. Now this becomes 0. Clear? Matrix substitution is wrong. This is 1 1 1. Yeah. Now what happens? N minus rank. So 3 minus this rank is 1. So this will be rank is 1, right? Rank of a minus I. A minus I rank is 1. Number of non-zero rows in grid is declared from 1. So 3 minus 1 is 2. So here satisfied, right? So therefore it is satisfied. So therefore, so conclusion. So therefore algebraic multiplicity of the eigenvalue 1 is equal to geometric multiplicity of the eigenvalue 1. So it is verified. Next one I have to verify second eigenvalue. Okay. So eigenvalue, same idea. Eigenvalue. What is next eigenvalue? 2, right? Second eigenvalue is 2. So for this again same. What I want, algebraic multiplicity, right? So algebraic multiplicity of the eigenvalue 2. So then go back, look at the characteristic polynomial or characteristic equation. So in that you can look at this is the characteristic equation, and lambda wants to hold for 1 is there here. Nothing is there means 1. So therefore algebraic multiplicity of the eigenvalue 2 is 1 here. So therefore here I can write so algebraic multiplicity of 2 is 1. Okay. Next I want geometric multiplicity. Second one, right? So for that I want a minus lambda I, then calculate this. So a minus lambda I. So what is lambda I here? Lambda is 2i. So this one directly I will write what is a minus 2i. What is a minus 2i? So this is matrix A, this is matrix A minus 2i. So so subtract, so minus 1 1 minus 1 1, this is 0 minus 2, because 2 minus 2, right? 2 minus 2, yeah, fine. And next one, r3 is modifying as r3 plus r2, and this is similar to minus 1 1 1 and 0 minus 1 0 and 0 0 0. That's it. And further you can proceed, multiply this second row with minus and first row with minus symbol, so that it will perfectly, and make this entry is 0. No problem. Okay, let us do that. Okay, simply, and next r1 also, at a time I am doing, r1 is modifying as r1 plus r2, r1 plus r2, r1 plus r2, then this become, then modify this, yeah, r1 plus r2, so minus 1 0 1. Okay, so next step, r1 is multiplying, r1 is modifying as minus 1 into r1. Okay, and r2 also modifying, r2 is modifying as minus 1 into r2. Okay, now so therefore this is similar to what do you get? R1 minus 1 into r1. So yeah, what do we get? First one 1 0 minus 1 1 0 minus 1. Okay, and 0 1 0 0 1 0 and 0 0 0. So this is perfectly reduced echelon form. So therefore conclusion is, what is the conclusion? So therefore geometric multiplicity of the eigenvalue 2 is, what is the nullity? Directly 1. So 1. So therefore final conclusion is, therefore algebraic multiplicity of the eigenvalue 2 is equal to geometric multiplicity of the eigenvalue 2. Look at here. Geometric multiplicity is 1 and algebraic multiplicity is 1. Here is 1, here is 1. That's why both are same. So therefore final conclusion is, so therefore algebraic multiplicities and geometric multiplicities of all the eigenvalues all the eigenvalues all the eigenvalues okay, are same. So algebraic multiplicity and geometric multiplicity of all the eigenvalues of the matrix A are same. So therefore A is diagonalizable. A is diagonalizable. Okay. And what is a diagonal matrix? Diagonal matrix is simply keep all the eigenvalues in the diagonal, principal diagonal, that is the diagonal matrix. So look at the problem number 5 and 4 here. What you observed is, look at problem number 5. So here the eigenvalues are repeated here. Here the eigenvalues are repeated and problem number 4 also eigenvalues repeated. Look at problem number 4. Here also eigenvalues are repeated. Here what are the eigenvalues? Here also eigenvalues same 3 3 4. Here eigenvalue is repeated, there also eigenvalue repeated, but this is not diagonalizable. But problem number 5, that matrix is diagonalizable. Therefore immediately what I want to say is, if the eigenvalues are repeating, we cannot say that it is not diagonalizable. We have to apply this theorem. So based on this theorem we can conclude whether it is diagonalizable or not. And with this I will stop. I will continue next class with a new concept.